mutual inductance. So mutual inductance and the self-inductance is almost same, with the small changes that self-inductance is the same coil, whereas the mutual inductance is because of the two different coils. Self-inductance is because of the same coil, whereas the mutual inductance is because of the different coils. Now let us say you have one coil, this is connected to the galvanometer, and you have another coil which is connected to the battery and a plug key. So this is called as the secondary coil, and the current and the coil in which the current is moving, it is called as the primary coil. Now let us say this has N2 number of turns and this has N1 number of turns. So whenever there is a change in the current coil, we know that when I close the switch and I say the current is moving, so in the coil when the current is moving, there is a magnetic field induced. There is a magnetic field induced in this direction. So whenever there is a magnetic field induced, there is a change in flux in the secondary coil, due to which there is a current induced, which we had studied in the coil and coil galvanometer. But this change in flux will give rise to the change in the induced EMF. So you will have it as N1, if you have talk about the number of turns, so you have the number of turns as N1 and N2. So you will have it as, let us take the general condition where you have it as N2 phi 2 is proportional to I1, where the current is in the primary coil I1. So this so this can be written as N2 phi 2 is equal to M times I1, or M is equal to N2 phi 2 by I1. So where if I1 is equal, or in general, M is equal to N phi by I. In general, the magnetic flux is equal to N phi by I, where N is number of turns and flux is the phi is the flux and I is the current. So with this we can say M is equal to the flux induced when I is equal to 1 ampere and the number of turns is equal to 1. So this is very similar to the self-inductance, but the difference is the current is moving in the one coil and the current is, the EMF, there is an opposing or the induced EMF opposing the growth of the current in that coil. So now we have the expression for induced EMF, which is equal to minus N times d phi by dt, which is equal to minus M times di by dt, or this, the magnitude of the induced EMF is equal to M times di by dt. So if di by dt is equal to 1 ampere per second, then the induced EMF is equal to the mutual inductance. The mutual inductance is numerically equal to the induced EMF in the secondary coil when there is a change in the current in the primary coil at the rate of 1 ampere per second.